Hello and welcome to Tensor Calculus Problem of the Day, posted on 7/14/2026. Okay, in the last video, we derived a tensor equation for the divergence of a vector of the field. It looked like this. Okay, and the Christoffel symbol was reduced to this. Then we expanded this to find the divergence in spherical coordinates, and we said, "Oh, that was a lot of work. There's 3 terms of this and 9 terms of that, so there's 12 total terms we had to go through here." So we said, "Oh, there's an easier way to do this, right? There's a better way." And that comes from matrix calculus, which I realize that is not exactly common knowledge, and it's called Jacobi's formula. Okay, for any invertible, you know what that means, differentiable square matrix A, the derivative of the determinant of A with respect to a coordinate is equal to the determinant of A times the inverse of A times the derivative of the matrix with respect to that same coordinate. Okay, I'm going to go out on a limb here and say this probably doesn't get a lot of use, but in this case it did. So in our case, the matrix is the metric tensor, right? It's our metric tensor from here. So, and the way they write the determinant of the metric tensor in the textbooks is just with little g. It means determinant of the metric tensor. Okay? So we can write Jacobi's the formula like this. So here's this part. In our case, it's the derivative of g with respect to the coordinate is equal to this part, g, the inverse, which is in our case, inverse metric tensor, and then the derivative of the matrix with respect to the coordinate. Okay? Now, here's what we want to do. We want to compare what this looks like to what we just had for the Christoffel symbol. Now look at this. Look at this term and this term, and look at this term and this term. It's the same, which is encouraging. All right, so let's take this equation here. Let's take that to the other side, divide through by 1 over g. And so we've isolated this. Now we can substitute that back in for the Christoffel, the symbol, and get this equation. Now this is a perfectly good equation. It's not that hard to use, but as I've said before, mathematicians cannot stop here. They have to keep going. So we will too. So to further simplify, we can say that what we have here is equal to 1 over the square root of g times the partial derivative of the square root of g divided by our, with respect to the coordinate, same coordinate. Okay. And now let's prove that real quick. Okay. What's the derivative of the square root of g with respect to a coordinate? Okay. So we bring the 1/2 down. Then we got g to the minus 1/2, which is 1 over square root of g. And then, excuse me, the derivative of what's inside, which is just g. Okay. So the square root of g times the square root of g is just g. Here's the 1/2. Here's this term. So they are the same. Okay. And the reason they want to do that is when they plug it back in now to the equation, which is what we're going to do. Oh, I'm sorry. The square root of g, this thing is called the volume element. That's what it's called in the textbooks, the volume element. Okay, so when we put this back in here, and once again, a perfectly good equation, but they cannot stop here either. So they factor out a 1 over the square root of g, which means I have to multiply this term by the square root of g, and then this goes away. That's right. So I'm just left with this. And the reason they did that, if you look at this for a second here, you will recognize that as a derivative of a product. And that's what they did. So here is the final expression that everyone uses in the textbooks for the divergence of V. It actually has a name. It's called the Voss-Weyl formula. Voss-Weyl formula. Two famous mathematicians. Okay? So, what are we going to do? Given the components of the metric tensor in spherical coordinates, which are these, find the determinant of G first, then find the volume element, the square root of G. Use that in this equation to find the divergence in spherical coordinates. All right, so we did this the long way last time. Now we want to do it using this new equation, the Voss-Weyl formula. All right, I'll post the result the day after. All right, see you later.